Now that we're near the end of our course, we can go back and see that there is some kind of connection here between several of the chapters. We have seen delta G, we've seen E sub 0, and we've seen KEQ, and we find out is that each of those can be converted from one to the other. So here's our little picture of our triangle, and this is showing that the equilibrium constant, the voltage of a cell, and the delta G can each give us kind of the same information, so we can convert one into the other. We'll come back and look at this triangle in a minute. When we're doing thermodynamics, okay, we saw delta G, and that was Gibbs free energy, and it tells us, how much a reaction is going to be product favored or spontaneous. And the idea of this is that if you have a nice negative delta G, or we'd say delta G is less than 0, then that is a nice product favored reaction. When we were doing voltages, then we found out if we end up with a positive voltage for a cell, then that was also a cell that was going to actually go forward. It would be product favored. And finally, a long time ago when we were doing KEQs, then we found out anytime a KEQ is greater than 1, then that is product favored. Because remember, our KEQ was the concentration of our products divided by the concentration of our reactants. And so if that comes out to be larger than 1, then we have lots of products. So we shouldn't really be surprised that there are mathematical connections between these three things, even though they come from 3 different chapters. Now, if we look on to the AP exam with our formula sheet, then we can find over here this little idea here. And so we see here's delta G, and that equals negative delta H minus T delta S. That's a useful equation. But here we have another expression. It's equal to, and so this is K from KEQ. So if we know the delta G, we can find the KEQ. So this is a nice equation. Delta G equals negative RT ln of K. So if we know the delta G, we can get the K. If we know the K, we can get delta G. Now what about R and T? Okay, well we know that this is going to come out in kilojoules. Okay, that's, delta G and delta H are kilojoules. And if we go back to the formula sheet, we're going to see, okay, here's R, and R can be given in joules. So this would be the value we use, and we have to be very careful here, because notice that the R is in joules, but our delta G would probably be kilojoules or needed in kilojoules. So there's going to be a conversion you're going to have to do. Now notice also what we have is here's delta G, and that equals negative NFE. So here is E0 from the electrochemistry chapter, and here's delta G again from the thermodynamics chapter. So those two are going to be connected. So we have another formula, and that's delta G is equal to negative NF E0. And the E0, then we're going to get that by taking the oxidation and the reduction voltages, putting those together. Now N, we saw that before, that is the number of electrons that were canceled when we put together the two half reactions. So the number of electrons transferred during any one reaction. And F is just a constant, and it's the Faraday constant, so 96,500 coulombs per mole of electrons. So when we see this here, if we see delta G is equal to negative NFE, okay, we can convert from delta G into the voltage, or voltage back into our thermodynamic delta G Gibbs free energy. Now we can finally see then that if delta G equals this and delta G equals this, then these two are equal to each other. And we can put that together and mush it around a little bit, and we will come up with an equation that we have on our title triangle, which has a lot of different variables. Or at 25 degrees, all those constants go in, and we end up with this equation. So the log of K is equal to NE over 0.0592. And again, N is the number of electrons that were canceled. Here's our voltage. Here's our equilibrium constant. So if you know E, you can find K. If you know K, you can find E. So these three connections are all in here using, again, R, which in this case is going to have to be 8.31, but this is volt coulombs. So notice that is 8.31 joules per mole Kelvin. It's 8.31 volts coulombs per mole Kelvin. And also, if we were to go back, instead of using atmospheres and torr, if we use kPa, it also comes out to be 8.31. So we can see that a joule is equal to a volt coulomb, just in case that ever comes up as something useful. So here's our final little triangle. If we know K, then we can convert it into a voltage for a cell, or vice versa. If we know K, we can get delta G. If we know delta G, we can get K. If we know delta G, we can get E0. So any of these three can be converted into the others using these formulas halfway through here. All these formulas are on the exam, on the formula sheet, so you can always go back and refer to them, and then at this point it's just kind of a plug and chug as long as you know what each of the variables stands for. And again, watch out for joules and kilojoules. R is in joules, delta G is going to be in kilojoules. And that's it.